So this video is the second in a series of videos introducing differential equations. In the first video, I talked about how to verify that a function is a solution to a differential equation, and I introduced the notion of an ansatz, or an educated guess, which helps you reduce the complexity of solving a differential equation to an algebraic equation. In this video, I'm going to talk about a little bit of the motivation and explain where differential equations come from. So the first example of where a differential equation comes from, it's quite a broad class of equations. Anytime you have a process that that occurs with equal probability, in a small interval of time, we get a differential equation here I'll write it down. dy dt equal minus a constant b times the original function y, or the unknown function y. And in this, where b is called a rate constant. Now the reason it's called a rate constant is that on its own it's not a rate. What a rate is the dy dt. So dy dt is the rate of change of y with respect to time. And in order to turn the right-hand side into a rate, you take the function y and you need to multiply it by something that gives you how many of y per unit time, and that's the units on b. So b is going to have units of 1 over time, and we call that a rate constant. And when multiplied by y, it gives you the rate, the overall rate. Okay, and I'm going to assume here that b is a positive value, just because, so depending on exactly what the process is, I have to say more about that. But the assumption here is that we have some process. You have a huge population of things, and in any moment of time, each one of them has an equal probability of disappearing. So the examples, you may have seen these before when you talk about exponential functions, radioactive decay. So here you have a whole collection of atoms, and in any moment of time, the probability for one of those atoms to decay and in a sense disappear, because it disappears as that larger molecule and breaks down into something else. So it disappears, and what you end up with is the number of particles left. So in this case, y is number of particles remaining. And it's going to satisfy this differential equation. Okay, and so as you probably know already, the solutions to this differential equation are going to be functions of the form e to the minus bt. So we're going to have an exponential decay when we have radioactivity being the source of this disappearance. Okay, another example that's not a great example, but it's a good one to bring up because it kind of fails a little bit to satisfy the assumptions that I put above. A light bulb burning out. So imagine we were in a building with hundreds of light bulbs. So we initially had, let's say, y is number of light bulbs. Number of functioning light bulbs. So what's the idea here? You turn on all the lights and you leave them on, and as time goes on, some of them will burn out and disappear, or they'll turn off. And so if the light bulbs worked the way described up here, then the number of light bulbs remaining that are on, or the collection of functioning light bulbs, will be described by dy dt equal minus b times y. Now this is not a terrible model, but it's not a great model like radioactive decay, because a light bulb tends to have an increased probability of dying out the older it gets. And that's because let's see, at least in incandescent bulb, you have a little wire in the middle of the bulb that heats up and gives off light. And with time, that wire can break down a little bit at a time. So it's much less likely for a light bulb to burn out in the first day after you plugged it in or turned it on than it is after the 1000th day. But if that process were not happening and this was just a spontaneous breakage that happened at any moment in its life, then this would be a good differential equation for the number of light bulbs remaining. Okay, another example is the removal of a drug from the blood or from the body. And this is a little bit more complicated in reality because the drug will be in the tissues, it'll be in the blood, and as it gets removed from the blood, it'll move passively by diffusion out of the tissues and into the blood. And so there's a slightly more complicated process going on. So this differential equation is not a great model for it, but it's not terrible. It does a good sort of first order or crude job of describing it. Okay. And so, but again, it's a similar thing. Any molecule of the drug that's in your body has an equal chance at any moment, in a sense, or if our assumptions were true and this was a valid model for it, it would have every molecule would have an equal chance and the same chance of disappearing in any moment. And so you would have exponential decay of the blood, of the drug from the blood. Okay, so the first one, the radioactive decay, is actually a very good model. This differential equation is a good model for it. The other two are not so good, but this is an important principle, is that we often assume processes are simpler than they actually are to make the model simpler. And in some cases, that simplification introduces problems that make our solutions unrealistic, but sometimes they preserve what we really care about. And so it's a matter of sort of modeling experience to figure out when it's okay to make these assumptions and when you're going to lose the important features that you want when you make these types of assumptions. And I won't say much more about that because that does take a lot of experience to sort of get a handle on. Okay, so in all these cases, the quantity y is the number of things left. And as long as they go in this very uniform type way, where there's no history, they don't know how old they are, they just go, if they're still around in the next second, they're just as likely to go as they were in the first second of their existence. And so I'm going to refer to this as spontaneous removal. And I'll refer back to this later when I talk about other examples. Okay, so let's go into another example, or another class of phenomenon that gives you a differential equation. This one I'm going to call self-driven growth. So what do I mean by that? So population growth is a good example. So if we start with a single cell, and it divides, and the time at which it divides, so I'm just going to say at some time. Now, what that time is, for this model to actually work out, that time has to be similar to the type of times that are chosen for radioactive decay, or the first model, except in this case, instead of the the items disappearing as these events happen. These are division events, so you get 2 cells instead of just 1 cell. And so, so now you have 2 cells. And then once you have 2 cells, either one of those could divide, and they're not going to divide simultaneously, they'll happen at random times. So you get 2 cells, and then 3 cells, and then 4 cells. And once you have 4 cells, you're going to accelerate how quickly you get new cells, because now you have 4 cells, any of which could divide in the next moment. So you have 4 times as likely, you're 4 times as likely to get a new cell. And so when you have a scenario like that, the differential equation that you end up with, and you can go through the analysis to get this, and I actually cover this. I probably have a video on my YouTube channel that covers this. For a different course, you get the equation dy dt equal b times y. And here again, b is a positive number, but this time it's representing a growth rate constant. Okay, so that's another type. So population growth is one way where the thing that you have is increasing in number, and that drives an even faster increase in numbers. So that's why you get exponential growth out of these models. Another example of this type of behavior is continually compounded interest. Where at every moment the bank gives you a small interest rate for every moment. So a millisecond after you invest your money, you get a tiny bit more money, and now you have a little bit more on which to gain interest. So just like when a cell divides, you now have 2 cells that could produce more cells. When you have money invested in the bank, as soon as you get the interest on that interest is put back into the account, so you now have more money on which to make interest, and it behaves just like population growing. Okay, so that is our second category of model. That gives you a differential equation. Here's another one that kind of combines some of the ideas already, or at least includes one of the ones that we've talked about already. So I'm going to talk about the category where you have a constant influx and spontaneous removal. Okay, so what are examples of this? So there's a a sort of classic place where this gets described, and you'll see this in a lot of early differential equation textbooks. So if you're pouring salt water into a vat, and it's well mixed. So as soon as the water goes in, whatever concentration you're pouring the water in at, it gets mixed in the tank right away. And you're letting out the well-mixed water. And you do that at the same rate, so that you don't end up accumulating or losing your fluid. So you're pouring in a certain amount per unit time of water, and that water is carrying salt, and then you're letting out a certain amount of water, equal volume, so that you don't overflow your tank or deplete all that's in there. And what's happening is, unless you let it go for a long time, at any moment you're going to be letting in more salt than is going out, or vice versa, depending on what the initial condition is for the tank. And you'll end up having this time-dependent behavior in the tank. Okay, so an analogous situation, another example. Having trouble flipping. Here we go. Another example. Administering a medication by IV drip. So that's when, you know, you're at the hospital and they put a needle into a vein, and you have a bag, and the medication is in the fluid in the bag, and that slowly but continually drips into the vein, and that's the way they deliver the medication to you. So that's going to be adding a drug or a compound into the bloodstream at a constant rate, and then simultaneously the body is removing it. And this is by spontaneous removal. So you have blood circulating around, and it has this medication in solution, and as your blood moves through, let's say, your kidneys, any of the molecules that are there have an equal chance of getting pulled out into the urine and getting removed from the body. So the body removes it by, and I'm going to call this spontaneous removal. So that process is analogous to radioactive decay. At any moment, any one of the molecules of medication in your bloodstream could be removed, just like at any moment a particle might undergo radioactive decay. And so the equation that you end up with in this case is dy dt equal, we have an addition, so we have a positive quantity A that's constant, and that represents the drip of medication into the body. And then it's removed by spontaneous removal, so we get a minus by. Now, for none of these will I go through a derivation, but a derivation can be, made for all of these, but it requires a little bit of probability theory and a bit more time to build up these equations. Okay, so that's our third category, the constant influx and spontaneous removal. And there's another one that gives us a similar type of equation, but it has sort of a different structure to it, and that is passive diffusion across a membrane. So I'll draw a little picture for that. So imagine we have a little vessel or a cell that's in the middle of an environment that has a concentration Y0, and then the barrier between the cell and the environment is this permeable membrane, and inside there's a concentration Y, but this stuff can come in and out across that membrane. So you can imagine if there's more stuff outside, then let's say it's salt. So if there's more salt outside, let's say sodium ions, those sodium ions will cross in and out spontaneously, just randomly, going across the membrane. But when there's more on the outside, there'll be more moving across to the inside than in the opposite direction. So whenever there's a high outside concentration, the inside concentration will go up. And whenever there's a low outside concentration, the inside concentration will go down. And so the differential equation that you get in this situation is dy dt, the rate of change of the number of molecules inside, is going to be a constant multiplied by the difference in the two concentrations. And we put the y naught first because when y naught is at a higher concentration than y, you want to go from the outside to the inside, so the y value is going to increase, and that means that dy dt should be positive. And if it's large minus small, we get a positive quantity here. And again, here, as in all the other cases, the constant that I'm introducing, C, is a positive number, and it's related to the permeability of the membrane. And y naught is the concentration outside. Okay. So the last example that I'm going to give is actually the only one that is what we call a nonlinear differential equation. All the other ones here, the nature of the function on the right-hand side, dy dt equal, is a linear function of y. You never have any squares or anything like that. And those are actually a much simpler category of function. So let's see here. Where am I at? Okay, so I'll do 5 up here. I have plenty of space. So the fifth one is an improvement on the population model. So you remember back here, I described this equation as one describing the population growth. This will give you exponential growth. This will have a solution e to the b times t, and that just continues to grow unbounded. And that's kind of an unrealistic situation because you always have resources limiting what a population can do. So this is where this new model comes in. So population growth with a slowing of the growth as the population increases. Okay, so what does that do? So first of all, we call this logistic growth instead of exponential. And the differential equation we get for this is dy dt. And I'm going to write it like the original, the first one, is equal to r times y. But I left a big space there so that I can replace what was r with r times something that changes. And so this entire expression you can think of as being a growth rate constant that multiplies y. Just like back here we had a growth rate constant that multiplies y. But here b was a constant. It didn't change. So we always got this exponential growth. In this case, what I'm going to do is I'm going to modify that constant by multiplying it by something that changes with population size. And it changes by decreasing. So when y is 0, this term is not in there, and the population builds like r times y, or b times y. So this is really, initially, we have an exponentially growing population. But as y goes bigger, it'll slowly erode away from y, and by the time y is getting close to the value k, which is another parameter, the population growth rate is going to decrease because 1 minus y over k gets closer and closer to 0. So you can think of this as still being exponential growth, but it's much slower. So the way this should look is you should have exponential growth at first, but then the exponential growth decreases and you get slower and slower growth. So it's going to deviate away from this rapid growth, and we'll see what we get when we solve differential equations like this guy. Okay. So those are the 5 different categories that I'm going to describe. I mean, there's many different things you can write down for these types of differential equations. There's things like force balance equations, which you get in mechanical problems, springs and masses and things like that, whole categories. But these are the ones that I'm going to focus on here because they have some kind of biological interpretation. And so let's just summarize all of those in one sort of list. So all of these have the form dy dt equal f of y. And what I mean by that is this is some function of y, so I can write it as an f of y. This is some function of y, so I can write it as an f of y. This is a function of y. This is, as I said, the first one where we end up with y multiplying y, and so we have some y squared in there. That's the first time we had y appearing multiplied by itself or anything of that type. So that's our first nonlinear case. And so in each of these cases, the f of y's, so we had f of y was equal to minus by, We had f of y is equal to b times y, where b is positive in both these cases. We had f of y is a minus by, and so on. And you notice this one, the cy naught minus y is, if you multiply this through and rename things, these two really have the same form. And then we had the logistic equation, where f of y was r times 1 minus y over k multiplied by y. Okay, so all of these have a special feature to them. We call all of these autonomous. And the reason they get this special name is because the right-hand side, the rate of change is what we have on the left-hand side, and then on the right we have a formula for what that rate of change looks like. And you'll notice that there's no t appearing in here. So that means that the clock time, if we look at the clock on the wall, it doesn't matter. If we start an experiment with, let's say, a bacterial population, I have a single bacterial cell. If that bacterial population satisfies this model, it doesn't matter if I start the experiment in the morning or in the evening. It's independent of the clock time. It operates autonomous of any kind of environmental inputs. So you can imagine how this would be incorrect if, for example, you didn't have good temperature control in your lab and it was colder in the lab in the morning and warmer in the afternoon. Then you would expect that the behavior of the population growth would change throughout the day, directly related to the clock time. And that would require that you have a t appearing in here, so we know that the dy dt is going to have to depend explicitly on the time of day. So when you have explicit dependence on time, we can have a differential equation. We can have a differential equation like dy dt is equal to, for example, let's say, for example, there's hormones often are not very successful if they're delivered at a constant rate. So some hormone delivery protocols, like hormone patches, have to have an oscillatory input instead of a constant input. So here you might have something like this. And this is replacing, in the IV drug example, it's replacing the A value. And now this depends on time. So the rate of delivery is going to oscillate throughout the day or throughout the week. And then you still have spontaneous removal of it, minus by. So this is a case where the function on the right-hand side, instead of it just being f of y, it's f of t and y. It has two independent variables. It depends on time and it depends on y. Okay, and these are called non-autonomous differential equations. And the reason I'm introducing that distinction is because I'm going to talk about slope fields in the next video. And I'll start off with an example of a non-autonomous equation so you can see the full generality of what a slope field can look like. But we're really going to be interested in primarily in these autonomous cases, and those are going to lead to an interesting sort of structure for analyzing these differential equations called the phase line, or in more general cases, the phase plane or phase portrait. Okay, so I'll end this video here, and the next one coming up will be about slope fields.